Hi, my name is Melly Beechwood. I'm with Northeastern University in the Computer Vision course for Spring 2026. Today we're going to be discussing a part of Principal Component Analysis, or PCA. On your last video, you have learned about eigenvalues, shorthanded to lambda here, and eigenvectors, what makes them special and unique from other types of vectors. You would have also learned the process of PCA and why it's so important when building an eigenspace. And then also about picking the most significant vectors and what that really means as you go. We're going to be learning about the eigenspace, what subspaces are, how to project an image into an eigenspace, and why does it even matter? So first up, what is an eigenspace? An eigenspace is a subspace for all eigenvectors for a specific eigenvalue, lambda. Now that's quite a mouthful. So what on earth does that mean? First off, let's address the subspace. Subspace is a subset of a larger vector set where three things are true. One, it must have a zero vector. Two, addition of two vectors within that space must stay in that space, in that subspace. And three, multiplication of those two vectors must also stay within that subspace. Oops. There you go. Now, that sounds a little weird, but you're actually more familiar with this than you might think. Think about the XY plane that we've been doing for a long time. This is a plane that has the ability to have vectors, so a point and magnitude. It has the zero vector, which is going to be here, and it has the ability to do it both addition and multiplication. So you might be wondering, curious, what is this a subspace of? Well, it's a subspace of the larger 3D, where we add our z-axis. So for the eigenspace, it's a subset of those eigenvectors associated with that lambda, but it's not all eigenvectors. So there can be different subspaces, different eigenspaces for all those different eigenvalues. And it's kind of a way to hold them all together. In practicality, though, what that means is that we're going to be imagining these, we're going to be storing them as an m-dimensional matrix. I'm going to just make a 3D tensor here. But now for the image projection, in this case, we're going to talk about how to project into that eigenspace, and I'm going to use our image, since it's a computer vision class, as our example. So what does projection mean? Projection just means that we how to put something into that space. So first, we're going to use a couple different steps. We're going to do kind of a step 0 here of processing the images. But you're going to want them in the same kind of position, so that way your variance between them isn't about the orientation, but it's the actual change in lights or the features on their faces. It's also critical when looking at eigenspaces, because we're looking at these vectors, that these images, when we do this, they're the same size. So that's another pre-processing step. Now, for the projection, what we're going to do first is we're going to get difference matrix. And this is done by subtracting our new vector from the mean vector, or in this case, the mean image. What that means in this case is if we had our mean vector, which is going to be kind of the mean, so the commonalities of all of the eigenvectors that currently exist in that space. So maybe in practice, this ends up kind of looking like, if we're doing eigenfaces, like kind of a blurry image that kind of shows the different features that humans typically have, like the eyes and maybe some hair, but it might have like a little bit of different types of hair, and it's just the mean within them. And then if we're wanting to project a new image within the space, say an image such as myself, where we've got a face, we've got glasses. Those are scary glasses, but that's all right. And short hair, we're going to subtract those from each other. So the mean, and this is our new. What that's going to give us is just the differences and the variation that is in that new image from the mean. So we can see that the mean doesn't really have a lot of glasses, but the body's pretty much the same, and maybe, I don't know, maybe that short hair is a little different or something. I'm not exactly sure what that would look like in this case, but it's all focused on what is the difference. Now the next step, so that is the end, this is our difference matrix. Now the very next step is going to be that we're going to multiply that difference matrix times our eigenvectors. And what that does is it reduces our matrix that's right now is just that difference, and it puts it in the same dimensional space as our eigenvectors. So in our last example, where I was just doing a 3D just because it's easier to draw, if we were only having 3 eigenvectors, a 3 by whatever the size of the vectors, dimensionality reduction. So because this is still going to be the same size, so this is still going to be an n by n here. And so what that does is that takes our new image times whatever our m dimensions are and gets our weights in that but that's going to be a size, it's going to be the same size as our other eigenvector, our matrix of eigenvectors. What this is the weights of this image for each of those eigenvectors. So how much does each one do? So why is this useful? What this does is it gives us dimensionality reduction and data storage, because we now have, instead of storing an n by n pixel, we've got a smaller space. We've done feature extraction. In this case, we noticed that the classes were different, and so that we've seen some more features, and a noise reduction. You're going to see this one more in the next video, where you're going to learn about how when you take it out of a subspace, that because of that mean image, it's going to reduce some of the noise. All right. Thank you for being here and learning a little bit more about eigenspaces and eigenvalues, and I hope it was enjoyable.